Now we are doing exercise for the moment generating function. First, I have the random variable u equals y plus z. And I want to find moment generating function. So moment generating function m u of s is the expectation of e to the s u. Now only u is random variable here, and we know it's e to the s y plus z. Now x, y, z are independent, which is also because it's independent. So it's e to the exponential sy times exponential of sz, which is the moment generating function of y times moment generating function of z with exponential and Poisson. You can either use the table from the website, from ECU Theory website, and you will get the answer. Final answer is this. Well, before that, let me write it down. Like the moment generating function of Bernoulli is 1 minus p plus p probability e to the s. Moment generating function of exponential function is alpha divided by alpha minus s. And the moment generating function of a Poisson random variable is exponential lambda es minus 1. Okay, next is also easy because we do the same thing like moment generating function of u. It's a function of s. It's expectation of e to the s times 2z plus 3. Oh, that's much easier because this is just e to the 3s times e to the expectation of e to the s times 2z, right? So it's s times 2z. So this moment generating function is exponential of lambda times e to the 2s minus 1. Now C is a little bit harder. We have the same formula and process. E to the expectation of e to the su also means expectation of sxy. Now I have two random variables. We can also use the law of total expectation. That means x and y, suppose they are discrete. Because x is discrete, so x is discrete, so I can have a total law of expectation. So this, I consider all x, the expectation of x given y equals y. Probability of, well, PMF of x. Why is that? So if we say that x and y are two discrete random variables, so take the expectation, I should have a double summation. Double summation and e to the sxy. Well, I'm thinking that here's not x, here's the e to the sxy. Okay. It should be this times the PMF, join PMF. Right. And this joint PMF, I can write it down like probability of x given y times the PMF of x. And now this turns what goes to here. This equals this. So now next page. Okay, I know that it is the expectation, the summation of x, expectation e x s x. I think I write it down wrong. So it should be e to the x x y x y x equals x. So that's x y given x equals 0 times the PMF of 0 plus if x is 1, probability of 1. So that is the expectations e to the 0 times 1 minus p plus expectation e to the sy times p. And then here is 1 minus p plus alpha divided by alpha minus sp. Well, I will write it on that again. It should be the summation of e to the sxy times the joint PMF and the joint PMF, this one, it's either probability of x given y times probability of y, the PMF, or y given x PMF of x. And then which one you want to use then depends on the question and your choice. And since now this question x is Bernoulli, so it's either 0 or 1. So it's easier to choose this one because x is either 0 or 1. If you choose this, then it's really hard because y is exponential, it's continuous. And part D. Well, I want to find the moment generating function of this disgusting expression. So it's expectation e to the s 2xy plus 1 minus x times z. Well, I have x, y, and z, and I know because x is Bernoulli, it's either 0 or 1. So I will use the law of total expectation for this one. So that is e to the s z. Well, I put u because this is u here, but given x equals 0 times probability of x 0 and x equals 1, probability 1. So now if I take 0 inside, then the first term will be expectation of exponential sz 1 minus p plus the second term is s times 2y only times p. Then you can find the formula, then it's 1 minus p times exponential lambda es minus 1 plus p alpha divided by alpha minus 2s.